Welcome to our deep dive, everyone. We're taking on Quantum Computing by Jozef Gruska. It's definitely a challenging read. But hey, isn't that where the real gems are hidden?
Absolutely. I think we can unearth some fascinating insights from Gruska's work for our listeners.
Let's start with the big why. Why bother with quantum computing at all? I mean, our computers now are already super powerful, right?
You're right, classical computers have done amazing things, but they hit a wall eventually.
Oh.
Yeah. Gruska gives this example of simulating a system with 100 qubits. A classical computer would need, well, more resources than there are atoms in the entire universe.
Whoa, okay, that's mind-boggling. So some problems are just too massive for our current computers, even the super powerful ones.
Exactly. That's where quantum computing steps in. It's not just about speed, it's a whole different way of thinking about computation.
Like a different approach altogether.
Right. Kruska highlights this quote from Andrew Stein. Stein talks about changing the program, like shifting our focus from individual particles to how nature itself allows information to be expressed and manipulated.
That's a really interesting way to think about it. It's not the physical stuff, but the information itself.
Precisely. And that leads us to the quantum world, which, as you may have heard, gets a little strange.
Bring on the weirdness. I'm ready for
Yeah.
Quantum Weirdness
All
101.
right. First up, superposition. Imagine a coin spinning in the air before it lands.
Yeah,
It's both heads and tails at the same time, right?
until it lands, yeah.
Qubits are like that spinning coin. Unlike classical bits, which are either 0 or 1, a qubit can be both at the same time.
So a qubit is in this in-between state, holding both possibilities. But how does it eventually choose a state?
Through measurement. When we measure a qubit, we force it to collapse into a definite state, either 0 or 1.
Ah, okay. So by observing it, we're actually influencing the outcome. That's pretty wild.
And it gets even wilder. Enter entanglement. This is where two qubits are linked in this, well, Einstein called it spooky action at a distance.
Spooky action.
Yeah, it means no matter how far apart they are, these entangled qubits can influence each other instantaneously. It's like flipping two coins that are linked. If one lands on heads, you know the other is tails, even if they're miles apart.
All right, entanglement definitely earns its spooky label. But how does all this quantum weirdness, this superposition and entanglement, actually give us computational power? How do we use these bizarre properties to solve problems?
The key is quantum parallelism. Because a qubit can be in multiple states at once, a quantum computer can explore many possibilities simultaneously.
Ah, so instead of going one step at a time, it's taking a massive shortcut, exploring all the paths simultaneously.
Exactly. Gruska uses the Deutsch-Jozef algorithm as an example. Imagine a black box, a function that takes an input and gives an output.
Okay.
This function is either constant, meaning it always gives the same output, or balanced, meaning it gives two different outputs equally. Now, a classical computer would have to test the function multiple times to figure this out, but a quantum computer, using superposition, can determine this with just one run.
It can analyze all the possible outputs at once. That's incredible.
It's a game changer, especially for certain types of problems. And this brings us to one of the most famous quantum algorithms, Shor's algorithm.
Shor's algorithm, the one that has cryptographers a little worried.
Exactly. It cracks a problem that's practically impossible for classical computers, factoring large numbers, which is, it's the basis for a lot of our current encryption methods.
So a large-scale, stable quantum computer running Shor's algorithm could potentially break the codes that protect our online transactions. That's a bit unnerving.
It's definitely something to consider. But that just shows how powerful quantum computing can be. Gruska also talks about Grover's algorithm, which is all about searching. Think of searching for a name in a massive phone book. A classical computer has to check each entry one by one, but Grover's algorithm can do it much, much faster using quantum properties.
So it's like having a superpowered search engine. What other types of problems can these algorithms tackle?
Well, that's what we're going to dive into next. We've talked about the why and a bit of the how of quantum computers, but actually building these things, that's a whole other challenge.
It sounds like it. From what I've read, building a quantum computer is like trying to, I don't know, sculpt with smoke. Incredibly challenging, but potentially game-changing.
That's a great way to put it. The challenges are huge, but so are the possibilities. Get ready to explore ion traps, nuclear magnetic resonance, even quantum dots.
I'm ready. From the theoretical to the seriously high-tech, it's all on the table. We'll be back in a moment to explore how researchers are trying to wrangle those quantum phenomena into a functioning machine. Stay tuned.
Welcome back. So, we've explored the why of quantum computing, gotten a taste of those mind bending concepts like superposition and entanglement, and now the big question, how do we actually build these things?
Right, because it's one thing to talk about these incredible concepts, these qubits and algorithms, but actually wrangling those quantum phenomena into a real machine, well, that's a whole other challenge. Gruska starts by talking about Benioff's quantum computer.
Yeah, he lays the groundwork by going back to those theoretical foundations. Benioff's idea, using qubits as the building blocks for a quantum Turing machine, it's fascinating, but it hits some roadblocks pretty quickly when we try to actually build it.
Roadblocks, like what?
Well, think about building a sand castle on a windy beach. The slightest disturbance can ruin everything, right? It's kind of similar with quantum states. They're incredibly fragile. Any interference, any little bit of heat or vibration can cause them to lose their quantumness. Gruska calls this decoherence, and it's a major hurdle. We have to shield these delicate states from any outside noise.
So it's like trying to build a house of cards in a hurricane. Every little disturbance could mess everything up.
That's a great analogy. And that's why researchers are exploring all sorts of different physical systems, each with its own way of trying to, well, to tame these wild quantum states.
Okay, let's get into specifics. Gruska talks about ion traps, which sounds super high-tech. What are those?
Ion traps use electric fields to trap ions, which are basically charged atoms. Picture tiny electrically charged marbles suspended in midair.
Okay, I can picture that.
These ions are trapped in a vacuum chamber, and we use lasers, these precise beams of light, to control the energy levels of these ions, essentially manipulating their quantum state.
Wow, so we're using light to control tiny particles in a vacuum chamber. That's some seriously precise work. What are the benefits of this approach?
Ion traps give us amazing control over those qubits, and they can hold on to their quantum states for a relatively long time. That's super important for doing complex calculations.
And they're actually working. We have ion trap quantum computers.
Oh, yeah. Some of the most advanced quantum computers we have today are based on ion traps. There are some incredible groups doing this work, like the team at the University of Innsbruck.
It seems like we're making real progress. But I'm guessing it's not all easy sailing. What are some of the challenges with ion traps?
Well, one of the biggest challenges is scalability. If we want to build a really powerful quantum computer, we need to trap and control thousands, maybe even millions of these ions. It's a massive engineering feat. And there's always that risk of the ions bumping into each other or interacting with stray particles in that vacuum chamber, and that can disrupt those fragile quantum states we're trying so hard to preserve.
So it's a balancing act. We need a lot of qubits to do serious computing, but adding more qubits means more complexity and more chances for things to go wrong.
Exactly. And each approach has its own set of pros and cons. Another fascinating technology Gruska dives into is nuclear magnetic resonance. You might know it as NMR.
NMR. Yeah, I remember that from high school chemistry. Isn't that what they use for medical imaging?
That's right. But researchers have found a clever way to adapt it for quantum computing.
Oh, that's interesting. How does that work?
So instead of trapping ions, we use a liquid sample that has a ton of molecules in it.
Okay.
And each molecule basically acts like a tiny quantum processor. We encode the qubits in the spin states of the atoms inside those molecules.
Spin states.
Yeah, it's a quantum property of atoms, and we use really precise magnetic fields and radio pulses to manipulate those spins to actually perform quantum computations.
So we're kind of using magnets to control the spins of atoms within these molecules. It's like a microscopic symphony going on in there.
That's a great way to picture it. And one advantage of NMR is that it can work at room temperature, unlike some of the other approaches that need these super cold environments.
No need for giant, expensive refrigerators. That's definitely a plus. But I'm sure there's a trade-off somewhere, right? What are some of the limitations of using NMR for quantum computing?
Well, one challenge is that the signal we get from those qubits is really weak.
Ah, I see.
We're measuring the average behavior of a huge number of molecules, so the signal from each individual qubit gets kind of lost in the noise. It's like trying to hear a single voice in a giant crowd.
So actually extracting useful information from those faint signals is a huge challenge.
Exactly. And that makes it tough to scale up NMR systems to a really large number of qubits. But even with its limitations, NMR has been a valuable tool for demonstrating those early quantum algorithms and exploring the basic principles.
It's really amazing to see how scientists are adapting existing technologies in these really creative ways to build these quantum computers. Gruska also mentioned something called quantum dots. What are those all about?
Quantum dots are these tiny semiconductor structures. Imagine these little islands that can trap electrons. They're kind of like artificial atoms, custom designed to have the quantum properties we need for computing.
Wow, so we're building our own atoms now.
In a way, yes. And one of the biggest potential advantages of quantum dots is scalability. We can potentially manufacture them on a large scale, kind of like how we make computer chips today.
So you're saying someday we could have quantum chips that are as common as the chips in our phones.
It's a possibility. But of course, there are still major hurdles to overcome. One of the biggest is figuring out how to control and entangle a large number of these quantum dots while keeping them coherent. It's incredibly difficult to keep these artificial atoms isolated from their surroundings and prevent them from interacting in ways that we don't want.
It seems like the more we cram into a system, the harder it gets to keep everything under control. So with all these different approaches to building quantum computers, ion traps, NMR, quantum dots, is there a clear winner in this race?
It's still very early days in the quantum world. The field is evolving so quickly. I think it's likely that the best solution might actually involve a combination of these different approaches, each one tailored for specific applications.
So it's not necessarily a competition, but more like a collaborative effort to find the best tools for the job.
Exactly. And the good news is there are brilliant minds all over the world tackling these challenges. I'm really optimistic about the future.
It's definitely an exciting time to be witnessing this quantum revolution unfold. But as you mentioned earlier, building the hardware is only part of the story, right? We also need to figure out how to actually program these quantum computers.
You got it. The hardware is incredible, but without the software, it's basically just a really expensive paperweight. And that's where the world of quantum algorithms comes in.
Okay, let's talk algorithms. We've touched on Shor's algorithm and Grover's algorithm. What other kinds of tricks can we program these quantum computers to perform?
Well, one area where quantum algorithms are showing a lot of promise is in simulation.
Simulation, like what?
Simulating complex systems like molecules or materials. It's a really computationally demanding task for classical computers, but quantum computers, because they operate on the same principles as the systems they're simulating, have the potential to do this much more efficiently.
So it's like having a perfect model of the system you're trying to study built right into the computer itself. That could be revolutionary for fields like drug discovery or material science.
You're getting it. Imagine designing new drugs or materials at the atomic level, all inside a computer. No need for those expensive, time-consuming lab experiments.
That's pretty mind-blowing. But what about decoherence? All those delicate quantum states, those qubits that are so easily disturbed? How do we make sure these algorithms can run without errors?
That's where quantum error correction comes in. Researchers are developing really clever ways to encode quantum information to make it resistant to noise. Think of it like shielding those fragile quantum states, protecting them from those environmental disturbances.
So it's like we're building self-healing quantum computers. If one part of the system gets messed up, the rest can compensate and keep things running smoothly.
That's a great way to think about it. And these error correction techniques are getting more and more sophisticated. Some researchers believe we're close to building fault-tolerant quantum computers. That would be a major breakthrough.
That's really exciting. But even with error correction, there are still going to be limits to what we can do with quantum computers, right? They're not a magic bullet that can solve every problem.
That's true. Quantum computers are not going to replace our classical computers entirely. They're more like specialized tools for specific types of problems, especially ones that involve complex systems or massive amounts of data.
So it's not quantum versus classical. It's about having the right tool for the job.
Exactly. And as we develop more of these quantum algorithms and really understand their capabilities, we'll get a better idea of where quantum computing can make the biggest impact.
Well, this has been a really eye-opening journey so far. The potential of quantum computing is just incredible.
Yeah,
But I have to admit, it's also been quite a mental workout trying to wrap my head around all of this.
I can understand that. It's a field that really challenges our intuitions about how computation works. It forces us to rethink some of our basic assumptions.
But that's what makes it so fascinating, right? We're on the verge of this new era of computing, an era that could revolutionize medicine, materials, science, artificial intelligence, maybe even fields we haven't even thought of yet.
I completely agree. Who knows what other amazing discoveries are waiting for us as we delve deeper into the quantum world?
Well, I, for one, can't wait to find out. A huge thank you to you, expert speaker, for being our guide through this incredible world of quantum computing. I know our listeners have learned a lot, and I certainly have too.
It's been my pleasure. I love sharing the wonders of quantum computing with others.
And to our listeners, thank you for joining us on this deep dive. We hope you've enjoyed this journey into the quantum realm as much as we have. So we've talked about the hardware, the challenges of building these quantum computers, and now it's time to dive into the software side of things. Quantum algorithms.
Yeah, this is where things get really interesting. We're talking about designing instructions that actually harness those quantum phenomena, the superposition, entanglement, all that.
Right. We've touched on a couple of those algorithms already. Shor's algorithm for factoring numbers, Grover's algorithm for searching databases. But what other kinds of problems can we tackle with these quantum tools?
Well, one area that's showing a lot of promise is simulation. Simulating really complex systems, things like molecules or materials.
I see, that makes sense.
Yeah, those simulations, they're super computationally demanding for classical computers. But quantum computers, they have the potential to do this much more efficiently just because they operate on the same principles as the systems they're simulating.
So it's like having a perfect model of the system you're trying to study built right into the computer itself.
Exactly. Think about it. We could design new drugs, new materials at the atomic level, all inside a computer. No more need for those expensive, time-consuming lab experiments.
That's pretty mind-blowing.
Yeah.
But what about decoherence, all those delicate quantum states we need for these computations? How do we protect these algorithms from errors?
That's a great question, and it's where quantum error correction comes in. Researchers are developing some pretty ingenious techniques to encode that quantum information in a way that makes it resistant to noise, to those disturbances from the environment. It's kind of like putting a shield around those fragile quantum states.
So it's like building self-healing quantum computers. If one part of the system gets messed up, the rest can compensate, keep things running.
Yeah, that's a good way to think about it. And these error correction techniques are getting more sophisticated all the time. Some people even believe we're on the verge of building fault-tolerant quantum computers, which would be a huge breakthrough.
That's pretty amazing. So even with these challenges, it seems like quantum computing has the potential to revolutionize a lot of different fields.
It really does.
Yeah.
And who knows what other incredible discoveries are out there waiting for us as we continue to explore the quantum world.
Well, I'm definitely excited to see what the future holds for quantum computing. And thank you so much for taking us on this deep dive. It's been an incredible journey.
It's been my pleasure.
And to all our listeners, thanks for tuning in to this deep dive. We hope you've learned a lot and maybe even been inspired to explore the quantum realm a little further on your own. Until next time, keep those quantum questions